Hello students, in this video I will be going over what a polynomial function is and then some generalizations that we can make as a result of some analysis. So let's take a look. So what exactly is a polynomial function? A polynomial function of degree n is an equation in one variable such that the expression takes on the form of some coefficient times x to the nth plus another coefficient times x to the some smaller exponent, and so on and so forth. So what you should be familiar with, it's not so much like memorizing this template here, because this template looks really scary. And the only thing that you should really be aware of is all of these a's here, they are coefficients and they take on real numbers. Okay, so they could be a fraction, it could be a decimal, it could be a negative number, positive number, rational, irrational, whatever you'd like. Okay, they just have to be numbers. They're coefficients. They're called coefficients. This last number over here, that's a term. The variables, okay, that the function takes on, usually in the form of x, but it doesn't have to be in the form of x. It could be t, it could be any variable you'd like. The only restriction is the exponents. The exponents which the variable is being raised by has to be a non-negative integer. So it could be 0, it could be any whole number, in other words. Okay, it cannot be negative. So what are some examples of a polynomial based on this definition then? Based on this definition, is the first equation a polynomial? Is the second expression there a polynomial? See if you can figure this out. Pause the video. Hopefully you guys had some time to think about this. So based on this definition there, the first expression is definitely a polynomial. The second is not, because the second expression there, I see variables there having exponents that are not positive, but we have negative exponents. Okay, so there are two classifications of polynomials. We can talk about polynomials that are even, that is an even degree polynomial. What exactly is an even degree polynomial? Well, it's a polynomial where the largest exponent of the variable is an even power. Okay? And conversely, we can have an odd degree polynomial. So, for instance, quadratic equation, right? The equation for a parabola, that is an even degree polynomial. So I have y is equal to, let's say, x squared minus 2x plus 1. That is an even degree polynomial because the highest exponent here is 2. Y is equal to, let's say, 3x minus 4. That is an odd degree polynomial because that right there is an odd degree. It's an exponent of 1. Another example of an odd degree polynomial, and we have not talked about graphing or working with this function yet, okay? But this is an example of an odd degree polynomial. Even though we have an even degree here, okay, it is not the highest exponent value. The highest exponent value is 3, and that is an odd number, thereby making this an odd degree polynomial. Why is there a need to distinguish between odd and even? Well, as it turns out, the behavior, and this is some of the generalizations that we can make based on whether or not it's odd or even. The generalizations that we can make is the end behavior. Okay, and what I mean by the end behavior is when we graph this stuff out, when we graph out an even degree polynomial, the end behavior will behave in one of two ways. It will either go towards positive infinity or go towards negative infinity, right? However, let me just focus in on this a little bit. When we graph out a polynomial, it will take on this like weird shape, okay? There will be highs and lows, there will be maxes and mins. Sometimes it will pass the x-axis and sometimes it won't, okay? But the idea is this, okay? When we talk about end behavior, as x goes towards positive infinity, meaning if I go in this direction here, right, the y values are going to go up. If I go in towards the negative infinity, I'm moving to the left, the y values are going to go up. So the end behavior is they're both going up, okay? They're moving towards positive infinity. So the end behavior is the same. Whenever we are graphing an even degree polynomial, the end behavior will be the same. So a way of thinking about this, and you've seen this before, wait, does this generalization apply for parabolas and quadratic equations? Absolutely, right? So a parabola takes on the shape of either a U or an N. And as a matter of fact, if you plot a fourth degree polynomial, okay, you're going to see many highs and lows, okay? It's going to take on these strange looking shapes. So these are some generalizations that we can make regarding even degree polynomials. And just like before, okay, where the leading coefficient in a quadratic equation, right, we have ax squared plus bx plus c, remember this, right? If a was greater than 0, it would be shaped like a U. Well, that's the same kind of behavior that's happening here. If a was less than 0, meaning the leading coefficient is less than 0, then the end behavior is going towards negative infinity. It's going below. And that makes total sense. So what about odd degree polynomial? An odd degree polynomial. An odd degree polynomial have opposite end behavior. Now what does that mean? So odd degree is going to look like this, where when x goes towards positive infinity, okay, we go down, okay, and when x goes towards negative infinity, we go up. They're moving in opposite directions. They're moving in the opposite directions. If a, the leading coefficient, happens to be less than 0, okay, this is the direction that we are going to go in. It's going to go in this kind of manner where when we head in a negative direction, negative infinity, y is going to go towards positive infinity, and so on and so forth. Okay, so what about when the leading coefficient is positive? Well, when x goes towards positive infinity, so will the y. When x goes towards negative infinity, so will the y. Y will also go towards negative infinity. Does this kind of behavior apply for linear equations? Absolutely, because if I have y is equal to, let's say, ax plus b, right, where a, again, is the leading coefficient here, okay, we also understand that a in this context here also kind of behaved like a slope value, right, for a linear equation, that is. So for when a is positive, the line is going to go in this direction here. So you see how x is moving towards positive infinity, y is also moving towards positive infinity. When x is moving towards negative infinity, y is also moving towards negative infinity. This is the same kind of behavior as what I am describing over here. Right? Similarly, if I say if a is less than 0, then the graph is going to go like this. Right? So when x goes towards positive infinity, y will go towards negative infinity. When x goes towards negative infinity, y will go towards positive infinity. And again, these are the generalizations that we can make about odd and even degree polynomials. All right. So, based on what I just told you, pause the video and see if you can answer these questions here. What degree are these polynomials, right? Find out whether or not the leading coefficient is positive or negative. And lastly, state the number of real roots you see based on these drawings. Hopefully you guys had some time to think about this. Let's take a look. Now, looking at this, I see that the end behavior is opposite, so that means this has to be an odd degree polynomial. Because it's moving in this direction, the leading coefficient here has to be positive. And I also see that we have 3 real roots. So therefore, this is an odd degree polynomial. the leading coefficient must be greater than 0, and there are 3 real roots. Let's take a look at the next one. The next one here, I see that it has to be an even degree polynomial. The end behavior is the same, right? The leading coefficient is positive because it's going up, and there are 4 real roots. The next one definitely looks odd because the end behavior is opposite, and the leading coefficient must be negative, and I also see that there are 5 real roots here. The last one, end behavior is the same, therefore it has to be an even degree polynomial because it's heading towards a negative direction. The leading coefficient must be negative, and there are no real roots. There are 0 real roots. Alright, so are there any kind of like real computation work that we have to do? Because in the first couple minutes of in the majority of the lesson thus far, everything that has been disclosed are really all theoretical and not many like things for you to work with. It's just things for you to recognize. So what are some things that you should know how to do for this lesson? So this is actually very similar to things that you already know. So suppose you have this p of x polynomial. Let's try to evaluate these 4 different statements here. Evaluate p of -1, p of 3a, p of a plus 1, and then the difference between p of a plus 1 and p of 3a. Pause the video to see if you can figure this out. So hopefully you guys had some time to think about this. P of -1. All you got to do is substitute wherever you see x. You're going to replace that with -1. And when we evaluate this all comes out to equaling to +8. Next, wherever we see x, I'm going to replace it with 3a. So it becomes 3a quantity cubed plus 4 times 3a squared minus 5 times 3a. And if we perform the necessary computation here, it reduces down to 27a cubed plus 36a squared minus 15a. Next, we're going to find out what p of a plus 1 is. Again, wherever I see x, I will replace that with a plus 1. Let's FOIL out a plus 1 cubed, and that is a major drag, I know, but so I want to do it in steps. So it's really a plus 1 times a plus 1 squared, which is a squared plus 2a plus 1. And then a squared plus 2a plus 1 again, because that's what a plus 1 squared is. And I distribute the 5, the -5. FOIL out this guy right here. I end up with the next expression, the transition, distribute the 4, and last step, I'm going to combine like terms. Wherever I see a cubed, I see that there's only 1a cubed. I see that there are 7a squared, and all combined together there are 6a's. The last term there, just the number, they cancel out. Last, I am to find the difference of those 2 functions evaluated. So I'm going to take what I've already found for p of 3a and p of a plus 1, and I'm going to perform the difference there. So I take a cubed plus 7a squared plus 6a, which is the equation for p of a plus 1, and I take p of 3a, which is 27a cubed plus 36a squared minus 15a, and I find a difference between the 2. Distribute the negative and combine like terms, I end up with this expression here.